Howdy, and welcome to Internal Combustion Engines lecture number 24. Okay, just a few reminders to get things started. First of all, please be reminded that your homework number 4 is due on Friday. That would be tomorrow, March 25th, and it's due at 11:59 p.m., uploading that to the Canvas website as we usually do. And then second reminder, exam number 1 is scheduled for Monday, March 28th. And for those of you that haven't had the chance to see the announcement yet, the exam number 1 will be a take-home exam. So I'll be releasing that at 9 o'clock in the morning, the usual start of class period or close to the start of class on Monday, March 28th. And you'll have 24 hours to complete the exam. So you'll have until Tuesday, March 29th at 9 o'clock a.m. The exam will be accessible through Canvas, and so it'll release right at 9 o'clock in the morning through the Canvas portal. I'll have a exam assessment, much like where you would find your homework in your labs and such. There'll be an exam portal that you can click on, an exam module, and the file will be there right at 9 o'clock in the morning. And then you'll have 24 hours to work it and scan it if you need to, and then upload your materials, your scanned materials to Canvas by 9 o'clock on Tuesday, March 29th, 9 o'clock in the morning, okay? So you'll have 24 hours for the exam. It is open book and open note, and, you know, really any reasonable resource, but is closed collaboration, right? So you can't collaborate with anyone, and that, of course, means not only collaborating with your colleagues in class, but colleagues outside of class, friends, internet discussion groups, right? It really needs to be reflection of your own work. And I know all of you are familiar with the Aggie Honor Code, so I don't have any concerns about you violating that. And if you have any questions about what could be potentially a violation of the Aggie Honor Code, reach out to me and I can help you sort that out. So related to that, your homework number 4, which is due tomorrow, Friday, is basically your sample for exam number 1, okay? So you want to make sure that you complete homework number 4, get that submitted by Friday night at 11:59, and then you'll be able to use that to prepare for exam number 1. The other item is that part of the reason why I made exam number 1 a take-home exam is I wanted to give you an opportunity to reflect more of your learning through a more extensive exam than I would have been allowed to do in the 50-minute period during class time. And so the exam that you'll have for a take-home exam realistically will take you about 2 hours. Okay, I don't expect it to take more than 2 hours. If it's taking substantially longer than 2 hours, then you might just be missing some major concepts that is causing it to take longer than that. It should be pretty straightforward for you to be able to complete within 2 hours. But you do want to give yourself that opportunity to spend about 2 hours working exam number 1 and scanning it and uploading it, okay? Okay, and then just another final reminder is that we do have part B of lab number 2 due next Friday. And so, hopefully that was one of the other reasons why I wanted to make exam 1 a take-home exam. I know that there's a lot coming due around this time of year, and so just to give you every opportunity to be able to distribute your workload accordingly and be able to balance everything. Just as a reminder, lab number 2, part B, is due next Friday, April 1st. Okay, so turning our attention now to where we left off on Monday, this past Monday. We were basically starting our open cycle analysis, and we talked about the additional processes that we add to the cycle to make it open cycle, to allow there to be a gas exchange process, an intake and an exhaust process. And how we started our analysis was at the end of process 3 to 4, so the process 3 to 4 that you were familiar with from before, which would have been the isentropic expansion process, for example. We ordinarily would have our contents after expansion, and then we would have a constant volume heat rejection process. But of course, as you now know, what we do at state 4 is we open our exhaust valve. And this second frame that you see in the picture that I've drawn here, right, these are the same pictures that I drew on the board toward the end of class on Monday. You can see that at state 4, essentially what happens is EVO occurs, exhaust valve opens, and then as process 4 to 5 occurs, there's a portion of the mass that was in the cylinder just prior to state 4 that escapes out the exhaust port. And then there's a portion of mass that remains, and the mass that remains, of course, expands and fills the cylinder volume at the rate at which mass is escaping out the exhaust port. Okay. So if you remember, when we talked on Monday, I asked you the question about what are the various irreversibilities that occur in thermodynamic processes, and we mentioned things like friction, and we mentioned throttling, we mentioned, well, we didn't mention it, but another irreversibility is mixing. A fourth type of irreversibility would be combustion. The second irreversibility that was mentioned was heat transfer through a finite temperature difference, right? So all of these irreversibilities essentially cause entropy generation, and we're doing an ideal cycle analysis, and we know that entropy generation is not an ideal thing, right? We don't want to generate entropy that is an indication of inefficiency within the process. And so we define this as an ideal blowdown process, but we also recognize that there's a tremendous amount of entropy that's being generated during this blowdown process by virtue of the mass that's escaping is initially at a high pressure. It's at the pressure of state 4, and then it dissipates, or it lowers its pressure to, say, atmospheric pressure, right? So just to highlight that, we can draw on our PV diagram, right? So we're basically here at that maximum volume. Piston is at bottom dead center, and our mass is at state 4, or our system is at state 4, which is at some elevated pressure P4, and we're essentially blowing down by allowing the mass to escape the cylinder to some exhaust pressure, right? Some pressure of the exhaust manifold. And so that pressure gradient, that pressure drop from state 4 to state 5 occurs because mass is escaping the cylinder. So you have less mass in the cylinder, same volume. And so consequently, the pressure lowers as the mass that remains fills that expansion, or fills that expanded volume. So the question is, well, if the mass that escapes is essentially a throttling process, we go from high pressure to low pressure without extracting any useful work out of it, right? That's an irreversibility. Then how can we model the blowdown process to be ideal, right? Well, this is where now we have to recognize that our system is open, and we're no longer doing what is called a control mass analysis, but we now switch to doing a control volume analysis, okay? So what do I mean by that? Well, just before state 4, so if you look at the figure on the left, this mass that's in the cylinder is a combination of the mass that will eventually escape and the mass that remains. And it's the same mass that we had at state 3, as at state 4, at state 2, as was at state 1. In other words, there was a series of processes where the mass didn't change because it was a closed system. And if you remember way back when we first talked about thermodynamic systems, we said that if we have a closed system, we can treat the mass of that system as our control mass. In other words, that is the mass that we're doing the analysis on, okay? The moment that we open the system, we can no longer do control mass analysis. In other words, our mass is changing. It's not staying the same. Remember, whenever you see the word control, it basically means something that stays the same, okay? So our mass is no longer staying the same, so we can't do control mass analysis. So instead, we have to do what is called control volume analysis. So rather than thermodynamically analyzing mass specifically, we're now analyzing a region of space, right? A portion of the universe that we're doing thermodynamic analysis on, okay? And so our control system basically becomes the region, and it's the same, by the way, it's the same control volume that we've always done. It's just, it's no longer able to be control mass analysis, but we're essentially analyzing the space that is bounded within the cylinder. Okay, so with the cylinder head at the top of the control volume, the cylinder walls as the side of the control volume, and then the piston, the top of the piston, as the bottom of the control volume. And by the way, even though we're calling this control volume analysis, that volume is allowed to change, right? So as we start analyzing these various processes, obviously our volume is going to change as the piston returns to top dead center during the ideal exhaust displacement process. So don't let that bother you. It's just that region in space that we're analyzing is what stays the same as what we're analyzing. Okay, bounded by those four walls essentially. Okay, so consequently, the mass that escapes is technically leaving our control system. So if it's leaving our control system, we actually don't care about it. If we were analyzing the condition of the mass that escapes, we would need to care about it, but we're not actually analyzing the condition, the thermodynamics of the mass that escapes. What we're doing is we're analyzing the mass that remains, because it's the mass that remains that is going to fill our control volume. It's going to be our control system, the mass that remains in our control system at state 5, right? So the figure on the right-hand side is showing you what we are analyzing at state 5, our control system that remains at state 5. So even though the mass that escapes is generating entropy, we actually don't care, because it's not generating entropy within our control system. It's generating the entropy as it's leaving the control system, and that's not our interest. What our interest is what happens within the control system, and that's the mass that remains. Now, what's interesting is the mass that escapes, right, is undergoing a throttling process, because at this point, right before it escapes, it's the pressure of the cylinder, and right at this point, for example, it's then immediately being lowered to the pressure of the exhaust manifold. So there's a throttling process there, an unrestrained expansion that is generating entropy. But what about the mass that remains? Well, the mass that remains is undergoing restrained expansion. In other words, the mass that is above it, which is the mass that escapes, is always in equilibrium with the mass that remains. So as a little bit of mass escapes, the pressure of the cylinder will decrease, the pressure of this mass will decrease, and that'll consequently allow the mass that remains to move up a little bit, to expand a little bit, but doing so with the pressure of the mass that remains to be in equilibrium with the pressure of the mass that escapes. Okay, and you can just sort of visualize that as all of this mass that escapes, the mass that remains essentially with its pressure in equilibrium with the pressure of the mass that escapes, just continues to expand and fill that volume, essentially pushing the mass that escapes out of the cylinder. Okay, and that then finally closes our discussion about how the mass that remains is not undergoing an irreversible process. It's undergoing a reversible expansion process. Okay, it's not generating entropy as it expands, the mass that remains, as it expands the whole volume, because it is transferring work to the mass that escapes. In other words, the mass that remains is what's pushing the mass that escapes out of the cylinder. So there's that push is a transfer of work for the mass that remains, and therefore allows this to be a reversible process, right? Now, we don't have to worry about that work transfer term, because we're not actually going to do a first law analysis of this mass that remains, okay? But, if we very rigidly wanted to, there would be a work transfer term where the mass that remains is what's responsible for pushing the mass that escapes out of the cylinder, and there's a work transfer there. And because that work transfer is present, it allows that mass that remains to have undergone a reversible expansion process, and therefore not generate any entropy, okay? And so finally, this mass that remains at state 5 is going to have the same entropy. So the entropy at state 5, because it's undergone a reversible expansion process, and because we also assume that it's an adiabatic expansion process, we can say that the entropy at state 5 is the same as what the entropy of its mass is at state 4, which would also be the same as the entropy of the mass that escapes. But of course, as that mass is escaping, just to beat a dead horse, I guess, as the mass that escapes has a higher entropy because it's generated entropy as it's undergone this throttling process, this unrestrained expansion past the exhaust valve, okay? So what that means then, looking at our PV diagram, is that at state 4, we have an entropy at state 4. And then finally at state 5, we also have an entropy at state 5, and this is equal to the entropy at state 4, okay? And so essentially, we can, if we draw this on, say, a TS diagram, for example, then our TS diagram would more or less look something as the follows, right, where we have our state 1, where we have relatively low temperature, low entropy. Oops, this is entropy, excuse me. Let me correct my subscripts here. So this is TS diagram. We have state 1, and of course, process 1 to 2 is an isentropic process where we increase our entropy from, or where we increase our temperature during compression, but we do so isentropically, so the entropy stays constant. We then have a some type of heat addition process, and so our entropy increases as a result of that heat addition process, and our temperature also increases, and so this brings us to state 3. And then we have our isentropic blowdown process where, we have our isentropic expansion process where we have work extraction, and during that work extraction, we also lower the temperature, and we do so isentropically, so the entropy at state 4 is the same as the entropy at state 3. And then finally, we have our isentropic blowdown process where we now have the entropy at state 5 to be the same as the entropy at state 4, okay? So this process 4 to 5, this ideal blowdown process, is essentially an isentropic expansion process, a continuation of the expansion process of the mass that remains, okay? So let me just go ahead and say that. The ideal blowdown process is a continuation of the ideal expansion process that is process 3 to 4, where even though the piston is not moving, the mass that remains expands isentropically to fill the whole cylinder volume as the mass that escapes leaves the cylinder. Okay? So very often we fix state 5 by saying that the pressure at state 5 is the same as the pressure of the exhaust manifold, and the entropy at state 5 is the same as the entropy at state 4, okay? Now, one thing I want to caution you on is that, and this is a common mistake, so let me just mention this caution. The volume, the total volume at state 5 is the same as the total volume at state 4, right? In other words, the piston is at bottom dead center. We're at maximum volume. But if you recall, specific volume, which is the total volume divided by the mass, is not the same at state 5 as it is at state 4. Okay, so specific volume at state 5 is not equal to the specific volume at state 4, precisely because the mass at state 5 is not equal to the mass at state 4, right? If we go back up here and look, we can see that the mass at state 4 is the same as the mass of the closed portion of the cycle. It's a combination of that mass that escapes plus the mass that remains, whereas the mass at state 5 is just the mass that remains, okay? And so we do just need to be careful about that, recognizing that the specific volume at 5 is not the same as the specific volume at state 4. Okay, but because this is an isentropic process, we can use the same isentropic relationships that we developed for process 1 to 2, the isentropic compression process, and process 3 to 4, the isentropic expansion process, right? And so we can use the same isentropic relationships for process 4 to 5 that we use for other isentropic relationships. So we can say, for example, that T2 over T1 is equal to V1, excuse me, just fix that real quick. There we go. I need to fix the whole thing. Okay. So we can say T5 over T4 is the same as V4 over V5 raised to the gamma minus 1. And we can say P5 over P4 is equal to V4 over V5 raised to the gamma minus 1, raised to the gamma. And then finally, we can say T5 over T4 is equal to P5 over P4 which is raised to the gamma minus 1 all over gamma, okay? Okay, so, and so this is of course true for, these relationships are of course true for any ideal gas undergoing an isentropic relationship where we assume that the ratio of specific heats are remaining constant during that process. Okay, real quick, just as a quick aside, before we move on and analyze our next process, process 5 to 6, there have been some questions about the relationship between a polytropic process and a isentropic process, right? So just as a quick sidebar, just recall that an isentropic process of an ideal gas under assuming constant specific heats that is gamma is constant during the process. So this isentropic process of an ideal gas, assuming constant specific heats, is a special type of polytropic process where N is equal to gamma, okay? So remember that a polytropic process is PV to the N equals a constant, which is to say P1 V1 to the N equals P2 V2 to the N. And so if we just manipulate this to say P2 over P1 is equal to V1 over V2 raised to the N, well, that's exactly what we have written up here, right? P5 over P4, it'd be, say P2 over P1 is equal to V4 over V5 or V1 over V2 raised to gamma, right? It's the same, it's of the same form, right? So these other relationships that you see here, T5 over T4 equals V4 over V5 to the gamma minus 1, well, that's, you can use those same relationships if it's a non-isentropic polytropic process, right? So in other words, we can likewise say T2 over T1 is equal to V1 over V2 raised to the N minus 1. Okay, that's a true statement for a polytropic process of an ideal gas. And likewise, T2 over T1 is equal to P2 over P1 raised to the gamma minus, N minus 1, N minus 1 all over N, okay? Okay, so I didn't explicitly highlight this. For those of you that watched the thermodynamics review lecture, I didn't explicitly highlight this in that review because this is only true for an ideal gas, okay? And I didn't want to make such a bold statement in the thermodynamics review in case it were to get used for a non-ideal gas situation, okay? But because this is an ideal gas and the ideal gas relationship of PV equals RT, right? It's this relationship that's causing these other relationships in terms of T2 with respect to volume and T2 or T with respect to pressure. The fundamental definition of the polytropic process is this one here, PV to the N is equal to a constant. That every polytropic process is defined as PV to the N is equal to a constant. But the moment that you allow your substance to be an ideal gas, well, now you can make these relationships between temperature and volume and temperature and pressure, okay? And so that's where the ideal gas behavior comes in. Okay, so let's move on then, and now move on to the next process, which is process 5 to 6. And so process 5 to 6, if you remember, is our ideal exhaust displacement process. And so essentially what's happening with the ideal exhaust displacement process is, of course, at state 5, so say, for example, this is our state 5. And this is our intake valve and our exhaust valves, right? Exhaust valve is still open. So this is our exhaust port, and intake valve is of course closed. Okay, And we have the mass that remains after the blowdown process that has now isentropically expanded to fill the whole cylinder volume. Well, now what happens in process 4 to 5, process 5 to 6, is the piston moves from bottom dead center to top dead center with the exhaust valve open, pushing the remaining mass out the control volume, out the cylinder. Okay, and so at state 6, we now have, again, our intake valve is still closed, our exhaust valve is open, and now our piston is at top dead center. So this is state 6. And then we have a different mass that now remains at the end of the exhaust displacement process. And that will be what we define as our residual mass, okay? And so the mass at state 6 is our residual mass. Okay? And so we can just go ahead and define at this present moment that mass at state 6 is the residual mass. Okay, we're going to come back to that residual mass here in just a little bit because that's going to define for us what we call the residual fraction, but we'll do that at the very end after we've described these other processes. Okay, and mass, this m sub r is mass residual as opposed to mass that remains, right? So I'm defining the mass that remains to be this mass at state 5 prior to the ideal exhaust displacement process. Okay, now your notes actually go through and essentially describe for you all of these different okay, just one moment here, sorry. There we go. Okay, so your notes actually go through and describe these various processes for you. So there's the ideal exhaust displacement process, right? And so you can see here, for example, where this is the mass that remains, right, is undergoing this continued expansion, this isentropic expansion process to the thermodynamic state 5, as opposed to what is being called state 5A, which is the state 5, the thermodynamic state 5 that is at the same total volume that is at state 4, right? And so this additional expansion that you see out to state 5 here, really to be precise, this is defining for us the specific volume. And so now, of course, you can see how the specific volume at state 5, there we go. You can see how the specific volume at state 5 is not equal to the specific volume at state 4, okay? And then we have the ideal exhaust displacement process, and you can see that there's quite a bit of mostly algebraic manipulation of the first law of thermodynamics in order for us to analyze the process 5 to 6, the ideal exhaust displacement process. I apologize, for some reason this isn't showing the different operators here, but this is, of course, dE CV by dt is equal to QCV minus the work plus the energy flow in minus the energy flow out. And your notes should reflect all the correct operators. It's just not showing up on my iPad. I apologize for that. But you can essentially go through this manipulation if you'd like. The one sort of algebraic trick that's being used here is that there's a point where we add the mass. So there's a point where we add mCpt to both sides of the equation, and that then allows us to combine terms at different states, right? And so ultimately we end up getting or excuse me, I'm sorry, I'm off by a process. This is not correct. This is for the ideal intake process, not the ideal exhaust displacement process. So anyway, you can go through this if you'd like, and ultimately the end result is that what is shown is that MCP dt by dt is equal to 0, right? This is the result from the first law analysis. And so when we have an equation like this, where you have terms on the left-hand side and then a term on the right-hand side that basically says all those terms are equal to 0, or excuse me, the product of those terms is equal to 0. Well, we know that mass, for example, would not be equal to 0 because that would be a trivial solution, right? Essentially a system that has no mass in it. We know that CP is not equal to 0. That's a material property. And so that would not be equal to 0. And so what the first law tells us is that the change in temperature must necessarily then be equal to 0, right? And so the non-trivial solution is that the temperature doesn't change during this process, which is to say that the temperature stays constant, okay? And so the temperature at state 5 is the same as the temperature at state 6, which is what we define as the exhaust temperature, okay? So if we go back to our notes, then we can basically fix our state 6 as follows. We can say that the pressure at state 6 is equal to the pressure at state 5, which is equal to our exhaust pressure. And then from our first law analysis, we also show that the temperature at state 6 is equal to the temperature at state 5, which we also call the exhaust temperature. Okay? And so those are our two independent properties at state 6, pressure at state 6, and the temperature at state 6. Okay, so now let's go ahead and do our last two processes. And if you remember when we discussed this in lecture on Monday, I separated these as two distinctly different processes. I said there was a process 6 to 7, which was the intake reversal, or the valve reversal process. In other words, our exhaust valve closes and our intake valve opens. And then I said there was the ideal intake process. Process 7 to 1 is our ideal intake process. But the reality is that there's no reason for us to separately define state 7. In other words, this state after the valves change positions, right? After the exhaust valve closes and the intake valve opens, there's really no need for us to necessarily know what's going on at that state 7, okay? And so we can actually combine that state into our process analysis and analyze what we would say process 6, 7, and 1, okay? And so that's what we're essentially going to do, and that's exactly what we do in the lecture notes, is we combine the process 6 to 7 with the process 7 to 1, and basically call it process 6, 7, 1, okay? Okay, so before we can do that, though, we need to go back and resolve this discussion that we started on Monday, but never really finished, in the context of the three different types of intake processes that we can have. Okay, so let me just real quickly go back to my notes and just kind of close that discussion. So if we go to slide 39, for example, you can see here where we have the three cases described. We have the unthrottled case, we have the throttled case, and then we have the supercharged case, or what I referred to as boosted case on Monday, okay? And so what is first shown in the diagram here, this first diagram, is the unthrottled case. And basically what you can see for the unthrottled case is that the intake pressure and the exhaust pressure are the same. And so the pressure at state 5 which is of course the same as the pressure at state 6, okay, is also the same as the pressure at state 7, which is the same as the pressure at state 1. Okay, the intake process, we haven't gotten to it yet, but process 7 to 1, the ideal intake process, is also going to be a constant pressure process. Okay, so if our situation is unthrottled, where intake pressure is equal to exhaust pressure, then it, in terms of how it looks on a diagram, it's not too terribly exciting because we have pressure at state 5, it goes to pressure at state 6, which is the same. We close our exhaust valve, open our intake valve. Now we're at state 7, and then state 7 is a constant pressure intake process, but it's at the same pressure as the exhaust process, and so that then brings us back to state 1, okay? We've already talked about the supercharged case, right? If you remember, this is what we were describing on Monday, right? The situation where the intake pressure is greater than the exhaust pressure. And so now you can see that we have our blowdown process go to state 5, which is at the same pressure as the exhaust pressure. We then have our exhaust process at constant pressure, which takes us to state 6. We then close our exhaust valve and open our intake valve. And when that happens, because the intake pressure is higher than the exhaust pressure, the higher intake pressure will force mass into the cylinder and cause the cylinder pressure to rise to the intake pressure. And so our state 7 pressure is higher than our state 6 pressure, which was at the same as the exhaust pressure. And then we have our ideal intake process at constant pressure, where state 1 then is at the same pressure as the intake manifold pressure. And then finally, we have the third case, which is the throttled case. And now in this situation, the exhaust pressure is greater than the intake pressure. And so we expand to state 5, where the pressure at state 5 is the same as the exhaust pressure. We then have our ideal exhaust displacement process, constant pressure to state 6. And then we now close our exhaust valve and we open our intake valve. And now this is where it gets a little interesting. But in this case, what happens is if you think about what's going on here, at state 6, our cylinder pressure, which is the same as the exhaust pressure, is higher than the intake pressure, okay? And so we close the exhaust valve, we open the intake valve, and because the cylinder pressure at that moment the intake valve opens is higher than the intake pressure, there will be some flow of mass from the cylinder into the intake port, right? Into the intake manifold. And so then you might think, well, geez, how do I define my residual mass? Because some of that mass left the cylinder in the process of 6 to 7 as I reverse these valves, as I close my exhaust valve and open my intake valve. But you don't need to worry about it, because when we start the intake process at state 7, process 7 to 1, the first bit of mass that enters into the cylinder is going to be the same mass that escaped when the intake valve opened, right? The same little bit of mass that flowed from the cylinder into the intake port is going to be the first mass that gets inducted as the piston starts to move from top dead center down to bottom dead center and draw that mass right back into the cylinder, okay? So that small amount of residual mass that seemingly escaped from the cylinder as we go from state 6 to state 7 is going to get inducted right back into the cylinder as we undergo our intake process, right? And so this first little bit of mass would be the residual mass that gets drawn back in, and then the rest of the mass that gets drawn in for the rest of the process is the fresh mixture, okay? The fresh fuel and air mixture, or fresh air, whatever type of cycle you're analyzing, okay? So that's our process 6, 7 to 1, right? What we do is we basically lump these 3 states together into a single process where we close the exhaust valve, open the intake valve, and then have the ideal constant pressure intake process from state 6, 7 to 1, okay? Okay, so that's our ideal intake process, and similar to when we were analyzing the ideal exhaust displacement process, we can do a first law analysis of this, our general open first law equation. And I apologize. I don't know why my operators aren't appearing here, but this equation, it'll reflect correctly in your notes, but this is dE by dt is equal to QCV minus the work transfer, work of the control volume plus energy that flows in with mass minus the energy that flows out with mass. Okay, now it's on this slide. I started to mention this on the exhaust displacement process and I got too far ahead of myself. But it's on this slide where what we do is we add an MCP-T term to each side of the equation. And that allows us to create a difference of MCP delta T, okay? And so by creating that MCP delta T, we're basically able to algebraically manipulate our first law equation, right? So this is MCP T1 is equal to M6 CP T6 plus this PI minus PE times the volume at state 6 plus mass at state 1 minus the mass at state 6 times CP T1, okay? So what we're essentially doing is we're essentially adding M6 CP6 T6 to both sides of the equation, right? And so that then creates an opportunity for us to have this differencing scheme in there that then ultimately allows us to algebraically manipulate an expression that finally gives us a relationship that says T1 is equal to the residual fraction, which we haven't defined yet. We'll do that in just a moment, plus PI minus PE divided by CP times the residual fraction times the specific volume at state 6 plus 1 minus the residual fraction times TI, okay, where TI is the intake temperature, okay? And so we can kind of carry this a little bit further and just do a little bit more algebraic manipulation. I won't go through all of this in great detail, but the end result that we want to get to is this bottom equation that we have here, which says that T1 is equal to 1 minus the residual fraction times Ti plus the residual fraction times Te, the exhaust temperature, times 1 minus pi over pe times gamma minus 1 all over gamma, okay? And so this is our ultimate final equation. And let me just kind of define some of these terms here. First of all, Ti is the intake temperature, which is the same as the fresh mixture inducted during the intake process okay? And note to bene, that Ti is not the same as T1, okay? T1 is the temperature of the mixture and I'm going to say the temperature of the trapped mixture because this is after the intake process and the intake valve is closed. So it's the temperature of the trapped mixture, where the trapped mixture is fresh mixture, that which came in that which was inducted during the intake process, the mixture that would have been in the intake manifold, plus the residual mass. And again, we haven't defined that residual fraction yet, but we will here real soon. Okay? And then finally, TE is the exhaust temperature. And so TE, of course, is the same as T6, which is also the same as T5, the temperature at the end of blowdown, okay? Okay, so let's talk a little bit about this residual fraction. And so that's actually defined for you earlier on slide number 44. And so you can basically see that the residual fraction is equal to, and this we've defined before, but it's equal to the residual mass divided by the mass of air plus the mass of fuel plus the mass of residual, right? And so the mass of air plus perhaps the mass of fuel would be what we were calling just a little bit ago the fresh mixture, right? And so that's the mass inducted during intake. And M sub r is the residual mass. And that is the mass oops, I didn't mean to do that. There we go. That is the mass that remains after exhaust, which would, in this development, be our state 6 mass. Okay? And so the total mass in the closed portion of the cycle, so the, or what I called later, just a little bit ago, the quote unquote trapped mass, right? Well, that is the mass which is equal to the mass of air plus the mass of fuel plus the mass of residual. And this is the same as the mass at state 1, which is the same as the mass at state 2, which is the mass at state 3, and then finally the mass at state 4. Okay, the mass during the closed portion of the cycle. Okay, okay, so you can see here that with this little algebraic description that's provided for you here, the residual mass is the same as the mass at state 6. The mass of air plus the mass of fuel plus the mass of residual is the same as the mass at state 4. And if you remember, we can define specific volume to be total volume divided by the mass, right? Total volume divided by mass. And so by using that relationship, we can then provide this relationship that we have where the mass at state 6 is the total volume at state 6 divided by the specific volume, and the mass at state 4 is the total volume at state 4 divided by the specific volume at state 4. And then relying on our ideal gas relationship where PV is equal to RT, which we can manipulate to say that the specific volume is equal to RT divided by P, we can then substitute this relationship for specific volume into that to our residual fraction definition where we have the specific volumes appearing. And so we can then show that the residual fraction ultimately is equal to 1 all over the compression ratio times T4 over the exhaust temperature times the exhaust pressure over the pressure at state 4. Okay, recognizing that the pressure at state 4 is not typically the same as the exhaust pressure. Okay, it happened to be that case in homework number 4 because we modified that cycle to be different, where the end of expansion lowers the cylinder pressure all the way to the exhaust manifold pressure, such that pressure at state 4 in that case is the same as the exhaust pressure at the exhaust pressure, right? But of course, in homework number 4, T4 is not the same as TE, and so you have to pay close attention to that. But this is how we define residual fraction, okay? And that basically completes our open cycle analysis and basically our chapter 3 analysis. And just the last little few slides that are in your notes, and again, I won't go through this largely because, again, the operators are not appearing for me in the various equations, but there is an example of how we do this open cycle analysis. And one of the items that you'll note is that if we start our analysis at state 1, right away we run into a problem of not knowing what T1 is, right? So in other words, if we look back at our equation for T1, we see that T1 is a function of residual fraction as well as exhaust temperature, right? And of course, residual fraction, if we go back to the construction that we just made, residual fraction is a function of T4 and P4. So prior to starting our analysis, we need to have information about state 4 before we can determine our temperature at state 1. And so we aren't able to explicitly determine state 1 at the start of our open cycle analysis. And so, well, what do? Well, of course, you've all had, at this point in your educational careers, you've probably had something like a numerical analysis course, and you know that in such a case, if you have to know something about what it is you're about to analyze before you can start the analysis, then what you do is you make a guess, right? So the first thing you do is, make a guess on the unknown values. And then iterate the solution. And so you would make a guess as to what your exhaust temperature is. You would make a guess as to what your residual fraction is. Use those guessed values in the equation for your T1 and come up with an initial guessed T1 and use that T1 to conduct your analysis until you get state information at state 4. And then once you have your state information at state 4, you can then iterate and plug those new values into your T1 equation and come up with a new T1, calculate again, right, and continue to iterate until you eventually reach a convergence of a solution. And so that's what this example that's on the last 3 slides of your notes does. It goes through this iteration process for you. And you can see that the last slide is essentially showing you the 3. So this particular example did 3 iterations where these were the guessed values for residual fraction and exhaust temperature. And so you use those 2 values to then go through and calculate these various values. And then you take your calculated TE and residual fraction values, and then you use those to be your starting point for the second iteration, come up with a new T1, go through and do your analysis again, come up with revised exhaust temperature and residual fraction, and plug that into your third iteration, come up with, again, a new T1, and do your analysis. And now at this point, you can see that your exhaust temperature, TE, only varied by 3 degrees, and your residual fraction varied by 20 thousandths of residual fraction, right? And so at this point, you can then say that you've reached convergence, right? And you can, at that point, stop the iteration, okay? Okay, so FYI, I will not ask you to do an iterative solution on the exam. That's not why I've decided to make it a 2-hour take-home exam. But you still need to know about this process. I may ask you a question about it, not necessarily asking you to do the iteration. But what's more important is the software that you're using for Lab 2 is in fact doing this iteration for you, right? So Lab number 2, that cycles software that you're using in Lab 2, is essentially going through and doing this open cycle analysis, right? It's going through and it's calculating information at states 1, 2, 3, 4, 5, 6, 7, and it's basing it all on some guessed initial residual fraction and some guessed initial exhaust temperature, going through and doing that iteration for you, and then ultimately converging to the solution and giving you an output, okay? And so what you're doing for lab number 2 is your software is actually doing this iteration for you every single time you change compression ratio and you change the cycle type, right? As you go from constant volume to constant pressure to the 2 different limited pressure cycles, okay? So you're not asked to do that, obviously. The software does it for you, but keep that in mind when you write your analysis for lab number 2 so that you understand now how that software is calculating these various parameters, what they're doing in those calculations. Okay, thank you very much for your attention. Sorry the video ran a little bit late, but I wanted to get to a good stopping point before your homework is due tomorrow and before your exam on Monday. And what we will do on Friday is we will start our chapter on combustion, chapter number 4. Okay, thank you all so much. Have a great day, and we'll see you tomorrow.